All right, so we're going to do chapter 2 review exercises. Let's go over this. Okay. In exercise 1, it says the commute time of 32 executives are listed below. Construct a frequency distribution table with 5 classes. Okay. In order to construct a table, you need the class width. And the class width is the maximum value, which is 75 here, minus the minimum value, which is 67, and then divide by the number of classes, which is 5. You will get 1.6. Remember, guys, you have to round up. So this is going to go to 2. And then how do you use the 2 to construct the table? You put the lowest value here, which is 67, and then you start adding 2 this way, vertically, not horizontally. You do it horizontally, it will be wrong. 67 plus 2, 69 plus 2, 71 plus 2, 73 plus 2, 75. Now, you need to figure out the number right here. With it's 1 unit below this number right there. So 69, 1 unit below will be 68. 68, and then start adding to the same way. For the frequencies, it should be easy. Just figure out how many values are there between 67 and 68 inclusive. I think I did that yesterday, so I counted 6 values. There are 6 values. And then you do the same thing for the rest. Now, to find the relative frequency, for the relative frequency, guys, you take this number right here and divide it by the grand total, which is 32. Now, be careful when you do your work online to just read carefully how many decimal places you have to round to. Because if it says 3 decimal places and you round it to 2 decimal places, you might get it wrong here. So just be very careful with that one.
I have a question for that.
Yes.
It's 0.188. I rounded the last number, so I had it 0.189. Is that right or wrong?
Oh, no, it should be 1.88, I believe. If I use your calculator, watch. Let's do it. 6 divided by 32. Probably I'm wrong. Let me see. No, 1.8. I got 1.875. If you round it to 3 decimal places, the 7 goes up to 8.
Okay.
But you can make it you can make it 1.9 if it says 2 decimal places. So it depends on how many decimal places you have to round it. And a lot of times people know how to do the work online, but they make mistakes in rounding. So guys, be very careful with rounding, please.
Okay, thank you.
Exercise 2. Students in my Math 141 class, summer 2016, were asked to rate how fearful they were of the course's statistics, statophobia. Using a scale from 0, absolutely no fear, to 10, extremely sympathetic, arousal, and crippling emotions, don't like stat at all. Here are the data from the male students. 5, 7, 7, 10. So the 4 students. Okay, find the mean and the median. That should be easy, guys. You can even plug it into the calculator and find the mean and the median, or you can do it, manually. When the mean and the median are very close together, guys, you can pretty much suspect that the shape of the distribution is symmetric. So whether you use the mean or the median, it doesn't matter. So shape, usually when the mean and the median are the same, are close together, that means the distribution is symmetric. Why? Because I did show you yesterday, when you have a bell-shaped curve, the mean, mode, and median are very much the same. All right, the next question. Here is the data from the female students. From 0, on a scale of 0 to 10, how fearful are you of the course statistics? So we got this data, 14 scores. The question is to find mean, median, mode, range, variance, and standard deviation. We could do that on the calculator, guys. This, I would do it on the calculator, definitely. There is a lot of data, and he's asking for the standard deviation. So let's do that on the calculator. So you go stat, edit, and I already have the data in there in L1, guys. So I'm ready to process the work here. Stat, calc, one variable statistic. And my list is in L1, so I need to choose L1. And then calculate. And here you go, guys. The first value X bar is the mean. I put 6.8 rounded to 1 decimal places. Now, as you can see, there is an S and there's an sigma. Since this is a sample of students, you use S. So S, the standard deviation is 1.4. Let's say you're asked to round to 1 decimal place, so it's 1.4. And then you have the median, which is 6.5. And you also get the Q1 and Q3, which he's not asking for. It doesn't give you the mode, so you have to figure out the mode on your own, guys. The mode here is the value that repeats most often, which is 6. The range is the maximum minus minimum. The maximum here is 9, and the minimum is 5, so 9 minus 5 is 4. Standard deviation is 1.4. The variance, guys, is the square of the standard deviation. So if you square 1.4, you will get the variance. So that's the variance.
I have a quick question.
Mm-hmm.
So on our assignments, you'll always tell us like how many decimal places to round to.
Oh, definitely. And online, it's inevitable that you're gonna know exactly how to round to. Otherwise, you wouldn't be able to input the answer. Yes.
Okay.
Yeah. So standard deviation is 1.4. Now about Z-score, couple questions about Z-scores, guys. Imagine that Sue Cash is a female student in your statistics class, and she got a score of 9 on the statophobia question. Using the sample mean and the standard deviation from the female students' data, find the Z-score. Well, the Z-score, guys, is the value minus the mean divided by the standard deviation. The value, he says, he gives us 9. And then we did the mean for the female students. It is 7.3, and the standard deviation was 2.1. You could do that separately, guys, if you want. Let me show you how to do this as well. Stat, edit. So I'm gonna put, 57710, it's already there. So let me just run stat calc, one variable statistics. I need to change my list to L2 now. All right, so the mean is 7.25 and the standard deviation is 2.06. So if I'm gonna round to 1 decimal place, it would be 7.3 and 2.1. So that is correct here. 7.3, 2.1. Actually, I need to change this. That's not correct here. And 2.1. All right. So in order to find the Z-score, it's the value minus the mean divided by the standard deviation. 9 minus 7.3 divided by 2.1. Okay, let's see what this one would be. 9 minus 7.3 is 1.7 divided by 1.4. And if you divide, guys, 1.7 divided by 1.4, you get 1.21. Okay. The next question, suppose you wanted to convert a statophobia score to a standard score, a system with a mean of 10 and standard deviation of 2. What would be the Z-score? Now he's telling us that the mean is 10 and the standard deviation is 2. Again, the Z-score is the value minus the mean 10 divided by 2, which is -1/2, which is -0.5. Let's go to the next one. Suppose that Sue is not a woman. You know what? I think that was correct here. I used the data for the male students here. So I'm just gonna make it a male student. That would still work because we got, and then here, a female. So we'll use the data from the female students. Suppose that Sue is not a man, but rather a female. Use the data from the female students to find her z-score. So now this is going to be correct, the 6.8 that I got. What was the data from the female students? Yeah, 7.3. So it's, what did I get for the male students? That's the data for the male students. We got it here. Yeah, so that should work right here. Exercise 5, guys. Find the 5-number summary. You can input this into your calculator and find the minimum Q1, Q2, Q3, and maximum. And I do encourage you to use technology, guys. But if the data is nicely arranged in order, I think it's faster to do it probably by hand. And I think I did arrange the data in order. How many values do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your median is going to be between the 5th and the 6th. 1, 2, 3, 4, 5. So it's between 53 and 67. That would be your median. It's halfway through, 53 plus 67, and then divide by 2. That's 60. Okay, that's the middle. Now I want to find Q1. Q1 is the value in the middle of the first half, right here. Well, you guys, you can see it must be 40. And the other one, it's going to be the third one as well, which is 73. So the minimum is 30. Q1 is 40. Q2 is 60. Q3 is 73. And the maximum is 93. What's the range? The range is the difference between the smallest and the largest. So it's 93 minus 30, 63. What's the interquartile range? IQR, which is Q3 minus Q1, which is 73 minus 40, 33. Now let's check if there are any outliers. So we're gonna go through the process just like yesterday. You take this value IQR and multiply by 1.5. What is 33 times 1.5, guys? 49.5. Then you take Q1 and subtract 49.5. Then you take Q3 and add 49.5. Okay, what is Q1? 40 minus 49.5. I got negative 19.5. Let me circle this value. And then Q3 is 73 plus 49.5, which is 122.5. Okay, here's how you figure out if you have outliers. Are there any values in the data set that are not between negative 19.5 and 122.5? Well, you guys, you can see all the values are below 122.5, so there are no outliers here. Any questions? Okay, that's how you figure out. If there was a value, let's say there was a value, you have 140 in the data set, then that would be an outlier because it's more than 122.5. Exercise 6. A student scores 62 on geography test and 285 on the math test. The geography test has a mean of 80 and a standard deviation of 15. The math test, however, had a mean of 300 and a standard deviation of 10. We want to know on which test did the students perform relatively better when compared to the rest of the class. In order to do that, guys, you have to convert to a z-score. The z-score for the geography test will be the value, which is 62, minus 80 divided by 15, which is negative 1.2. For the math test will be 285 is the value, minus 300 divided by 10, which is negative 1.5. Actually, the students did not perform well in either one because his z-score is negative. But which one is worse? Well, the higher the z-score, the better. Which one is higher? Higher means larger values. It's the negative 1.2. So better on the geography because the z-score was higher. Although in practice, the students is below the average in both classes. Okay? So that's question 6. We're gonna go to question 7. Okay. You have a box plot, and you guys, you're gonna help me answer some of the questions, or at least tell me why the answers make sense that you see there. Okay, this is a box plot that represents the cost in dollars of 12 CDs. Which cost is in the upper quartile? Upper quartile is the highest quartile, which is a Q3. And yesterday I explained to you guys that this is a Q3, this is a Q2, this is a Q1, this is the minimum, and this is the maximum. So upper quartile means a Q3. Just read it. That's the 25. And he labeled them, scaled them one at the time. So that should be a 26. And that's why I put 26 in here. Okay. What is the range? What is the range of the cost? The range is the maximum minus the minimum. The maximum is the last value and the minimum is the first value. Well, if you read it, guys, that should give you 29 and this one should give you 7. So the cheapest CD is $7 and the most expensive one is 29. 29 minus 7 is 22. What's the median? Median is right here. It looks like it's halfway between $20 and $21. That's why I put 20.50. Which cost represent the 100th percentile? 100th percentile is the last biggest value in the data set, which is at $29. How many CDs cost between $14.50 and $26? Where is $14.50, guys? It's right here. And $26 is right here. And my answer was half of 12. How did I know that? Any students can tell me, how do we figure this out? No, Q1 is not the 26. Q1 is actually 1450. The 26 is the upper quartile, which is a Q3. Somebody is asking me about Q1. Okay, any ideas? How do we know that there are 6 CDs? I said half. It doesn't give me that information, but from the graph you can tell. It says how many CDs cost between $14.50 and $26. Okay, let me tell you why. This is the 25th percentile, guys. And this is the 75th percentile. What's the difference between 25% and 75%? It's 50%. So half of the data, guys, are inside the box. Well, I have a 12 CDs total, so half of 12 will be 6 CDs. And for your information, a quarter of the data is right here. From the minimum to Q1, we get a quarter. And from the Q3 to the maximum, we get the other quarter. And from here to here is a 25%, 25%. So actually your box plot, guys, is split up into 4 quarters. First quarter, second quarter, third quarter, and fourth quarter. And that's why this is 6. How many CDs cost less than $14.50? Okay, we just said that. This is $14.50 Q1. We said from Q1 to the minimum is a quarter of the data. Well, I have 12 pieces, 12 CDs. What's a quarter of 12 will be 3. and that's why I put 25% of 12, which is 3. Okay, I'm gonna move on. 8, we're almost there. A movie theater recorded the number of tickets sold daily for a popular movie during the month of June. The box and whisker plots shown below represent the data from the number of tickets sold in hundreds. Which statement can be made about this? It says the second quartile is 600. Well, that's not true. The second quartile is 400, guys. The mean, we don't know the mean. From the box plot, you cannot tell what the mean is, so you can never answer this question. You can find the median, but not the mean. The range is 300 to 600. That's not true. The range starts at the minimum of 100 and a maximum of 900, so that's not true. This is not true, not true, not true. Let's see, the last one probably must be true. 25% of the attendance is between 300 and 400. Watch, guys. This is 300 right here, and this is 400. And I just explained to you, every single piece of the box plot is 25%, so that is a 25%. This is another 25%. This is another 25%. And this is another 25%. So that is the true one. 9, the box and whisker plot can be used to compare the annual income of 3 police officers. Based on the box and whisker plots, which statement is true? Let me show you the statement. Right, there's the statement right here. Let's see which statement is correct. As you can see, I picked 2, but let's see why the other ones are not correct. The median income for nuclear engineer is greater than the income of all the musicians. Okay, the median income is right here for the nuclear engineer. Is it true that this is greater than all the incomes of musicians? Look at the incomes of a musician, guys. They go from here all the way to, that's not true. This musician right here makes more than the median income of a nuclear engineer. So that's not true. The median income for police officers and musicians is the same. Would you guys agree that this is the answer? Look, this is the median for police officer, and this is a Q2 for a musician. They are exactly the same, so that is a true statement. Let me show you that the other statements are not true. All nuclear engineers earn more than all police officers. Well, the nuclear engineers, yeah, earn more, but not more than all police officers. Look, this police officer right here, guys, earn more than this guy right here. So that's not a true statement. The last one, a musician will eventually earn more than a police officers. Well, it looks like, yeah, they'd be earning more, but not all of them. There are some of them maybe will not get a raise. There's a musician right here, maybe right here, that's the maximum salary that he or she will get. They will never make it, you know, just beyond this one. So we don't know. We don't know about that. We cannot say yes for this one. Okay. And the last question, use the stem and leaf plot to answer the following question. This is a stem and leaf that represents Ben's test score for the year. What's the median? Okay, what I did here, guys, I just rewrote the data set. 65, 68, 72, 73, 73, 73, 78, 73, 81, 83, 83, 86, 87, 96, 99, and 99. How many pieces of data we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So your median is going to be between the 8th and the 9th. Count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's between 79 and 81. Halfway through will be 80. And that is the median. All right. So that is, I will scan this and email it to you later today, guys. So if you want to use it separately. All right. What is a probability experiment? Is an action or trial through which specific results, counts, measurement responses are obtained. For example, you roll a die and get a 6. That is an experiment. Now, what is your chance of getting a 6? Not 100%. There are 6 faces on the die, so your chance is only 1 out of 6. This is a probability experiment. Or you toss a coin, a quarter, and you get a head. This is a probability experiment. Now, what is your chance of getting a head is not 100% because there is a head and a tail, so your chance is 50-50. Outcome. The outcome is the result of the experiment. For example, if you roll a die, guys, you don't know what the outcome is going to be. It could be 1, 2, 3, 4, 5, or 6. So these are called the outcomes. Now, you would win if you get 6. Your chance of winning is only a 1 out of 6 because there's only 1 6 in there. But you don't have control of the outcomes. The outcomes could be any number on the face of the die. What is a sample space? A sample space is the set of all possible outcomes of a probability experiment. So for example, when we roll a die, your sample spaces could be 1, could be 2, could be 3, could be 4, could be 5, could be 6. And we write it as a set like that. The notation for the sample space, they use the letter S for sample space. Event. What is an event? Event consists of one or more outcomes, and it is a subset of the sample space. For example, you roll a die, you would win if you get an even number. So what are the numbers that would work in your favor if you get an even number? If you get 2, you would win. If you get 4, you would win. And if you get 6, you would win. So 2, 4, 6 make your event. So event that what works in your favor. Here is an example. I put roll a die. Outcome is 3. So you would win if you get 3. That's an outcome. The sample space for a die, guys, as I listed above, it's 1, 2, 3, 4, 5, 6. Event, the face on the die is even, so it's 2, 4, 6. If I put odd here, it will be 1, 3, and 5. Okay, let's do another example. A probability experiment consists of rolling a die and tossing a coin. Describe the sample space. Okay, can you guys, I need your help now. So help me list the outcomes. If you roll a die and toss, just let's say a penny at the same time, what would be the outcomes? Can you guys start helping me list them? What would be the first one? Yes, I'm waiting. What do you expect to see when you roll a die and toss a coin?
If you roll a die,
together. No, you got to do them together. So you started, okay, 1 with the head. Does that make sense?
Yeah.
2 with the head. 3 with the head. 4 with the head. 5 in a head. 6 in a head. But it could be also what, guys? 1 tail, 2 tails, 3 tails, 4 in a tail, 5 in a tail, 6 in a tail. If you count them, guys, how many are there? There are 12 outcomes. You don't do it separately. This is an experiment that we're doing 2 actions at the same time. Now I'm going to show you a very easy ways to figure out the number of outcomes. If you roll a die, you have 6 outcomes. If you toss a coin, you have 2. Well, you guys, you notice if you multiply 6 by 2, you get 12, and that's what we got. So that's how you can figure out how many do you have to list. So rolling a die, tossing a coin, and the number of outcomes is 12 outcomes. Okay, here's a question for you guys. If I roll 2 dice, how many outcomes are there? 2 dice.
24.
Not more than 24. How many would you get on the first die? 6, right? How many would you get on the second one? 6. What's 6 times 6?
36.
Okay, let me show you that it is indeed 36. I'm going to start listing them. 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6. 2 with 1, 2 with 2, 2, 3, 2, 4, 2, 5, 2, 6. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, and so on and so forth. So if you can figure out the number of outcomes from the first action, the number of outcomes from the second action, multiply the two, you get what you need, which is the total number of outcomes. Simple event is an event that consists only of one outcome. So if there is only one outcome in an event, it's called a simple event. Okay. What about if I toss 3 coins, guys? 3 quarters. How many outcomes are there? Each one has 2 outcomes, head or tail, head or tail, head or tail. So that would be what? 2 times 2 times 2, which is what?
8.
8. Okay. So that will be 8. And let me list them for you. You get 8 outcomes, and you want to know why? I'm going to list them. Head, head, head. You could get this. Or you could get head, head, tail. Or you could get head, tail, head. Or you could get head, tail, tail. You could get tail, tail, tail. You could get tail, tail, head, tail, head, tail, and tail, head, head. Can you guys think of anything else? Impossible. These are the only possibilities. Well counted. 1, 2, 3, 4, 5, 6, 7, 8. You don't need to list them to know how many. It is, each coin has 2 outcomes. 2 times 2 times 2, guys, will be 8 outcomes. And this is what takes us to the fundamental counting principle. If one event can happen in M ways and another event can happen in N ways, the 2 events together, guys, can happen in M times N. So we never add, it's always a multiplication. Because I always ask this question to students, said, roll a die and toss a coin. How many outcomes are there? So they say a die has 6, a coin has 2, 6 plus 2, 8. No, it's 6 times 2, which is 12. And let's do this example together in here. You are purchasing a new car. The possible manufacturers, car sizes, and colors are listed. So you could get a Ford, GM, or Honda. Your car size could be compact or mid-size. Your color could be white, red, black, and green. How many different choices do you have, guys? Can you tell me how many choices you possibly have here? Okay, for the manufacturer, how many choices do we have? You guys agree? 3, right?
Yeah.
And for the car size, how many choices do we have? 2.
2.
And for the color, how many choices do we have? 4. And what's the sign that has to go in between? Multiplication. 24 ways. So you could buy a Ford that is compact, that is white. A Ford that is compact, that is red. A Ford that is compact, that is black. A Ford that is compact, that's green, and so on and so forth. I'm not gonna count them, guys, but I know I have 24 ways of doing this. Okay. Types of probability. Let's give you the definition of probability now. The probability of an event is, by definition, guys, is the number of favorable outcomes, what works on your favor, divided by number of possible outcomes. We'll do examples on this so you can understand how probability works. You roll a six-sided die. What's the probability of each event? Rolling a 3. So can you guys help me? What's the probability of getting a 3? You write the probability like this: P, capital letter, getting a 3 equals a fraction. Okay, how many 3s are there in a die, guys? There's only one 3. So what works in your favor, it's only one. And how many faces does the die have? 6 faces. So it's 1 out of what? 6. That would be the answer. Now I want the students to tell me what's the probability of rolling a 7 on a die.
0.
0. There is no 7. So if someone asks you, let's play this game for money and you would win if you get a 7, don't play it, guys, because you're going to lose every time. So that's a 0. Event C. What's the probability of rolling a number less than 5? So what's the probability of C? I could have put A, B here. So probability of C. Okay, you know the denominator does not change, guys. It's always a 6 because you have 6 faces on the die. That's what I mean by number of possible outcomes. That's okay. Less than 5. What do we have less than 5? 4, 3, 2, 1. So I have 4. So the answer is 4 out of 6. That is what the classical definition of probability is. We'll do some more examples as we progress in this. Now, there is another definition of probability using frequency tables. I'm going to put the definition and show you how to use it. It's very easy. Sum of all the frequencies. So the grand total should be always in the denominator, guys. It's if your probability is based on observations obtained, from a survey or from an experiment. This is called the statistical probability, sum of all frequencies, and here the frequency of the event. Just like a relative frequency that we did in chapter 2, this is called empirical probability. And let me show you how to use this one. A company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade. So far, 1504 people have been surveyed. What's the probability that the next person surveyed has a positive overall impression? So probability of positive impression. Okay, can you guys help me out? What's the denominator here? You agree that the denominator should be the sum of all frequencies. That's what I put in there. So 1504. The numerator is what works in the favor of getting that probability. He wants a positive impressions. Well, which one are positive impression? Right here, 408. And that's your answer.
That
Any
says
questions? Yes. Any questions?
That says 406.
Oh, 406, yeah. You're right. 406 divided by 1504. If you're doing the work online and ask you to do 2, 3, usually probability is at least the 3 decimal places, just divide and put the 3 decimal places. Okay. Let's continue from here. What about if I ask you what's the probability that the next person surveyed will have a negative impression? So you just put 752 divided by 1504. You're going to notice the probability can never exceed 100%, guys. You cannot go beyond 100% in probability, and you cannot go below 0. You always have to have 0. 0 is the least value that you get. Like, let me give you an example that the answer is 0. What's the probability that today is Thursday, guys? Well,
0.
0. When the event is impossible to happen, then the probability is equal to 0. Now, what is the probability that today is Wednesday? Is 100%. It's 1 equals 1 because today is Wednesday. So why do we do probability? We use the probability when we are not certain about what's going to happen. So we try to estimate, you know, and figure out a percentage. But if we're sure about what's happening, there is no need, you know, to do probability. Weather forecasting, guys, is a probability because they cannot tell you for sure that this is a fact. That's why they can never tell you it's 100% sunny. They always, you know, just use a percentage just in case that their forecasting, you know, just doesn't turn out to be 100%, you know, accurate. So weather forecasting is another example of probability. Law of large numbers, as an experiment is repeated over and over, that when you repeat an experiment so many times, the empirical and the classical definition of probability become the same. Now, there is a third type of probability, guys. It's not very important to us. It's based on guesses, intelligent guesses. It's based on intuition, educated guesses, and estimates. For example, a doctor may feel a patient has a 90% chance of full recovery. When like someone goes to a doctor for a surgery and they ask the surgeon, you know, what's my percent that my surgery will be successful? The doctor will say 95. They never say 100% because they want to protect themselves. So they say 90%, 95%, 80%. Sometimes they tell you if it is a back surgery, 50%. This is all based on past experience, educated guesses, intelligent guesses. They're not based on actual experiments where they bring 10 patients and perform the surgeries on them. You cannot do that on humans. So this is an example of subjective probability. Another example of subjective probability is when financial analysts, when they predict, you know, just an increase or decrease in a stock market, these are based on guesses. That's why if they were facts, everybody will go and invest in the stock market. But because they're based on intelligent guesses, they could be right or could be wrong. What we're gonna do, guys, now we learned three examples of three types of probability. We're gonna match each example with its type. Classify this statement as an example of classical, empirical. So remember, empirical from a survey, from a table. Classical is just the classical definition of probability, and subjective is based on the guess. What do you think of number one, guys? The probability that you will get the flu this year is 0.1. Would it be classical, empirical, or subjective?
Empirical.
What I hear somebody else saying what?
Subjective.
Subjective. How do they know that we're gonna get it's just a guess, 10%. They say there's a 10% you'll get a flu. This is just a prediction, just a guess. Probably they're predicting the weather will be better, no germs, no viruses, just like what we're having today. So this is a guess, guys. The probability that a voter chosen at random will be younger than 35 years old is 0.3. What do you think of this one? Voter, that means you go and survey them. So that's gonna give you what here? It's gonna be what? The empirical. Classical, guys, you don't make up. You have possible outcomes and you have favorable outcomes. Number three is going to turn out to be classical. The probability of winning 100 raffle tickets is 1 out of 100. You have a raffle, it has 100 numbers, and one of the numbers is a winning numbers. So the probability of winning will be there is one number that's winning. That's what works in your favor, 1 over 100. That is an example of a classical definition. Okay. Range of probability. As I told you, the probability must be between 0 and 1. You cannot exceed 100%. I'll give you an example that I gave to my students a while ago. I said, what is wrong? Is there anything wrong with saying I made 120% efforts in this class? Well, almost everybody answered this correctly except for a few. One student said, no, there is nothing wrong with doing that. Well, yes, there is. Everything is wrong with saying that. It's impossible for you guys to go beyond 100% capacity. Your capacity is 100%. So you cannot make 120% efforts. 120% goes beyond you. So it's 100% is the maximum. And all I wanted the students to say that this is a violation to the definition of probability, because the probability has to be between 0 and 1. When I mention percent, guys, it's the same thing as probability. So when we say what's the probability or what percent, it's exactly the same thing. Now, here's a question for you. If the probability it's going to be sunny today is 90%, what's the probability that it's not going to be sunny today? Can someone answer that? So the chance of being sunny today is 90%. What's the chance that it will not be sunny?
10%.
How did you figure this out?
100 minus 90.
Exactly. So the probability of the event plus the probability of the event not happening, they should add up to 1 always. So if E is an event and E prime is the complement of the event, means not E. You are correct. The probability of not E plus probability of E should always add up to 1. So you guys, if I ask you the probability that you're gonna win something is 75%, I could ask you easily, what's the probability that you're gonna lose? Well, if 75% of your chance of winning, 25% if is your chance of losing. The two probabilities have to always add up to 1. Okay, that's another. Next. You survey a sample of 1,000 employees at a company and record the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34 years old. So how do I do this? Probability of not between 25 and 34 years. Okay, who can help us answer this one? What's the probability of selecting someone who is not between 25 and 34? What do I do? That's considered an easy question, guys.
1,000 minus
360,
366.
exactly. You could, yeah, you know, the 366 is what we don't want. So we want the rest. And as you said, it's 1,000 minus 366. Always divide by the big number here. Some students will do it this way. Say 54 plus 233 plus 180 plus 125 plus 42. Yeah, that's fine. You can do that. But 1,000 minus 300, that will do it. So that will be what? 634 divided by 1,000. And usually you'll be asked guys to round to 3 decimal places. That's a probability. Okay, here is another question. What's the probability of selecting someone who is between 55 and 64 years? Who is between 55 and 64? You guys agree it should be 125 divided by 1,000. Okay. Example. Your college identification number consists of 6 digits. Let's see if you can help me with this. Each digit can be from 0 to 9, and each digit can be repeated. So your college ID number could be, for example, 1122778. You can repeat digits. What is the probability of getting your college identification number when randomly generating 6 digits here? Sorry. Okay, guys, let's say my ID is 1, 2, 3, 4, 5, 6. And I go to the calculator and I ask the calculator to generate 6 digits for me, a number that has 6 digits. What is the chance that when the calculator does that, I'm gonna get my ID? It's gonna show me 1, 2, 3, 4, 5, 6. You know, the chance is gonna be very, very low. It's not gonna happen. It's just like winning the lottery. How do I figure out this? So can you help me find the probability of something like that happening? Any ideas? So there's only one ID number that matches your numbers, your ID number. So actually it is a 1 here. Your chance of winning what works in your favor is 1 ID. Now I need you to help me figure out what are the possible numbers of IDs that the college can generate here. He said that the ID can be 6 digits and the digits can be anywhere from 0 to 9. So how many choices do we have for this digit here from 0 to 9? How many choices are there?
Like 10?
10. Do you guys understand why 10? Because the 0 is included. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10. Same thing here, 10. 10, 10, 10, and 10. And what do I do to figure out, you know, just the total number of outcomes? We multiply them, guys. Remember, this is the counting principle. What's a 10 times 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 a 10? It's a million. So the chance, guys, that you go to a computer program and ask that computer program to pick 6-digit number, and that 6-digit number is going to be your ID, your unique ID, it's only 1 out of a million, just like winning the lottery. And later, guys, once we finish this chapter, I'll show you what would be your chance actually of winning the Powerball if you play it. You will see. It's going to be very low. But why people keep playing? Because it is not 0. It's very close to 0, but it's not 0. All right, next. Conditional probability. A probability of an event occurring given that another event has occurred already. That's what a conditional probability. So we're gonna, the way I set up the questions in my math lab are based on a table. So I would like you guys to pay attention, you know, just to the way we're gonna do this exercise, because once you pick it up, you should be able to do all problems related to conditional probability. Conditional probability, he'll ask you to find a probability, but he'll impose a condition on you. He said, I want that condition to be met first. So that's what conditional probability. The table shows the results of a study in which researchers examined a child's IQ and the presence of specific gene in the child. Well, before I do the questions, let's make sure that we understand how to read this table, guys. Okay, this is a table. This number, guys, represents the total number of children surveyed. It's a grand total. It's called grand total. Now, let me tell you what 52 means here. You can see the 52, it's at the end of the row of high IQ. So 52, it tells you that there are 52 children who have high IQ. 50, there are 50 children who have normal IQ. Now, let me tell you what 30 here means. 30 means children who don't have the gene present. 72, children who have the gene present. Now, can someone tell me what 33 means here? The 33.
Children with high IQ and have the gene.
Exactly. It's the children with high IQ and with the gene present. 19, guys, means the children who have high IQ and the gene not present. So it's the intersection between the high IQ and the gene not present for the number 90. Okay, guys, let's answer the question if we understand how the table works. Find, okay, I'm gonna do part B first. It's the easier part. Find the probability of selecting a child with normal IQ. Okay. No conditions here. He's not saying anything. He says, what is the chance of picking a child from the group of 102 will get someone with normal IQ? Well, we know the grand total, guys, is what? 102. And how many children are there with normal IQ? 50. Do you guys agree with this answer should be 50 divided by 102? Remember the definition of probability. Total number of outcomes, possible outcomes, which is 102. Favorable outcomes. Now, what do you mean by favorable? Favorable to the normal IQ. Well, I have 50 students who have children who have normal IQ, so it will be 50 divided by 102. Next question, which is a new question now. Find the probability that a child has a high IQ given that the child has a gene present. So he's putting us a condition that you must, just pick a child who has the gene present. What's the probability that this child will have a high IQ? I'm gonna pause.
33.
What did you say the answer would be?
Would it be 33? 33 over 102.
What do you guys think?
Yeah.
That's not correct. Well, the numerator, yes, it is correct.
52 over 102.
No, the numerator is correct. We want, you picked 33 because it says it has to have the gene and a high IQ. How many children have a gene and a high IQ? It's 33. That is correct. The denominator is not 102. He says, guys, find the probability that a child has a high IQ given, he's putting a restriction on us, that the child has the gene. He wants us only to pick from the groups of children who have the gene present. So we cannot pick from the group of students who don't have the gene. That's a condition on us.
So over 72.
19.
72. How many children have the gene present, guys? It's 72 right here. So here's how this works, guys. I'm gonna give you a very easy shortcut to it to figure out the answer when you see it. Okay, look how well I would figure the answer if I were you, and I would like you guys to use this for part C. What comes after given goes to the denominator. What comes after given? The gene is present. So just count the total. Always count the total of the gene. Well, the total of a gene present is 72. So it just goes to 72. Now, what goes in the numerator? In the numerator is the intersection between the high IQ and the gene present. Well, the intersection, guys, high IQ and gene present is right here. You just do this, do that, and then where the two meet will be your numerator. So always what comes after giving, this set has to go to the denominator. And every time he gives you giving, guys, you do not do the grand total anymore. You just have to follow, the restriction that he gave you. So let's look at part C and see what happens here. Find the probability that the child has the gene, given that the child has an high IQ. Okay, so you understand, guys, this has to go here. So what goes in the denominator here?
33.
No,
50.
grand total of the high IQ.
Oh,
It has to be the grand total of the high IQ, which is what?
52.
52. And now intersection between gene and high IQ, which is the same thing, 33. So it is 33 divided by 52. Exactly. Let me give you another question. I'll write it down. D. What is the probability of selecting a child with gene present giving normal IQ. Okay, what would that be? So, given normal IQ, so we're only selecting from the group of students who have normal IQ, not all 102 students. How many total students do we have with normal IQ, guys? 50. Okay, now I want the intersection between the gene present and the normal IQ. Look, guys, this is the normal IQ. This is the gene present. Where do they meet? At 39. It's 39 over 50. Does that make any sense? Any questions here? So this is how we find conditional probability. That's what a conditional probability is. If he doesn't say given, guys, your denominator is everything, the whole thing. But once you put the given restriction, then your denominator has to change, you know, just to this restriction as well. I'd like, you know, just to really understand, you know, just this table and refer back later to it. I put some more questions later, you know, just in this handout to better grasp, you know, the concept of conditional probability. All right. Next, independent events. Let me tell you what, when we say two events are independent. Two events are independent if the occurrence of one event does not affect the probability of the occurrence of the other event. I mean, the word independent, whatever it means, this is what independent is. In probability, it means the occurrence of one of the event does not affect the probability of the occurrence of the other events. If the events are not independent, guys, we say that they are dependent. Let me give you some examples to give you a better sense, you know, of what independent events are. Decide whether the events are independent or dependent. Selecting a king from a standard deck of cards, which has 52 cards. Not replacing it, that's the first event. And then selecting a queen from the deck, that's the second event. Do you think the two events are dependent or independent? Before you answer this question, guys, I hope that all of you are familiar with the standard deck of cards. The standard deck of cards has 52 cards. It has 4 kings. So the probability of selecting a king is 4 out of 52. And the probability of selecting a queen is 4 out of 52 always. So we select a king from a standard deck. What's the probability of selecting a king, guys? It's 4 out of 52. We do not replace it. That means the card that we withdraw, we keep it on the side. We don't put it back. Do you think that will affect the probability of selecting a queen? If I want to find the probability of selecting a queen here, guys. So the probability of selecting a king, it's going to be 4 out of 52. What is the probability of selecting a queen if I don't replace the card? Can someone help me here?
Is it 4 out of 51 now?
Very good. So that means the probability, the normal probability of a queen has changed. And the definition of independent events, it says the occurrence of one event does not affect the occurrence of the other event. So this did change. So that means the events are not independent, dependent. Can you guys change one word in this example and then the events will become independent again? Selecting a king from a standard deck and then what? Instead of the word not replacing it, what do you say? Replacing it, put it back. If you put it back, the probability of selecting a queen will be again 4 out of 52. So that was not affected. Then the events will be independent. So I'm going to give you another example. I don't know if I listed that here, but I gave to students last semester. Here's another example. You have a jar that has candies, 15 pieces of blue candy and 15 of red candy. You pick one candy the first time. That's your first event. And you want a blue. The second, and you eat the candy. Then you pick a second one, and your second event, you want to pick a red one. Are the events independent? The question was no, because the first time you pick a blue candy, the probability was 15 out of 30. For red, I have 15 red. It should be 15 out of 30 if I don't interfere. But since you ate, just that piece of candy, you're not working out of 30 anymore. You're working out of 29. So that changes the probability. In this case, the events are dependent. What do you think of those two events, guys? Tossing a coin and getting a head. That's the first event. Rolling a 6-sided die. You know that tossing a coin and rolling a 6-sided die, they're two different, devices, two different experiments. They have nothing to do with each other. So definitely the two events here are independent. Let me show you some more examples of independent events from the book, because I wanted to understand this well in chapter 3. There you go. I'll just project it under the screen. There you go, guys. It's on page 153. What about number 10, guys? Do you think the events are dependent or independent? Returning a rented movie after the due date, that's the first event, and receiving a late fee, that's the second event. What do we think? Dependent, because you receive a late fee as a result of being late. You see how the two events relate with each other? These are dependent. What about 11? A father having hazel eyes and a daughter having hazel eyes.
Dependent.
Dependent, because yes, it's in the genes sometimes, that is dependent. 12. Not putting money in a parking meter, that's the first event, and getting a parking ticket.
Dependent.
Dependent, because if you don't put money, you're going to get a ticket if you get spotted. 13. Rolling a 6-sided die and then rolling the die a second time so that the sum will be 5 on the two dice. Dependent, because if you get 6 on the first roll, you will never get 5, guys. So it all depends on what you're going to get on the first roll. If you get 1 on the first roll, you need 4 on the second one. If you get 2 on the first roll, you need 3 on the second one. So they depend on each other. And you guys can see number 9. This is the one that I put in the handout. So just to give you a feel of what dependent and independent events are. Okay. Let's go back to this. We'll be done soon. All right, just a few more things. Okay. If two events are independent, the probability of the two events happening together, A and B, it's the probability of A times the probability of B. And I'm going to give you an example, show you an example here. A coin is tossed and a die is rolled. What's the probability of getting a head and then rolling a 6? I'm going to show you 2 ways to do this, and I'm going to show you that this formula would work here. So a probability of rolling a 6 and tossing a head. Okay. Let's list the outcomes, guys. Since I'm doing those together, let's list the outcomes. You could get 1 with the head, 1 with tail, 2 head, 2 tail, 3 head, 3 tail, 4 head, 4 tail, 5 head, 5 tail, 6 head, 6 tail. Okay, I want a 6 and a head. Well, this is the only one that has a 6 and a head, guys. So you guys agree with me that the answer should be 1 out of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But let me show you that we could have done this way. We know rolling a die and tossing a coin are independent events. So this one, you could write it, probability of rolling a 6 . One second. Plug in the power for my computer. All right. Probability of rolling a 6 times probability of head. Okay. If you roll a die, guys, what's the probability of rolling a 6 just by itself? Can someone tell me what's the answer? Should be what? 1 out of what? 6. What's the probability of rolling a head, getting a head when you toss a coin, guys?
1 over
1 over
2.
2.
Multiply them. What do you get? 1 times 1 is 1. 6 times 2 is what? 12. So you get the same answer. So if the events are independent, guys, the probability of 2 events happening together is the probability of the first event times the probability of the second event. I think we have time just to do part A. So I'm just going to do part A for this, and then we'll continue the rest of the chapter tomorrow. So let's just do this. And then, guys, if you have access to a printer, again, you can download this, print it. Otherwise, I'll email it to you, and I will email chapter 2 this afternoon to you. The probability that a knee surgery is successful is 0.85. What's the probability that the doctor performs 3 knee surgeries and that they are all successful?
Is it 3 times 0.85?
Okay. Let's see. If I listen to you.
Oh, it'll be over 1.
Very smart. Good. So that means wrong. It's wrong. It's not 3 times 0.85. You guys agree that those 3 patients, they're independent of each other. They come from different places. They'll be put in different rooms. So these are independent. If they are independent, guys, since we're doing 3 surgery, find the probability of success of each surgery and multiply them all together. Well, we know the probability of success is what? 0.85, right? For the first patient, times 0.85 times of the second patient, and times 0.85 for the third patient. Let me just do the math. I know it's tempting to do 0.85 times 3, but that will take you over 1. That's impossible. So I got 0.614, guys, as you can see. Okay, I'm gonna change this. That none of the surgeries are successful. That's bad news for the doctor, for the surgeon. Okay. What is the probability that none of the surgeries are successful? Let's do this, guys, and we wrap this up. So the doctor performs the 3 surgeries. What's the probability that he's going to goof on all 3 of them. None of the surgeries will be successful. That's very unlikely to happen, guys. You're going to see the probability is going to be very low for this happening. Okay, any ideas? What's the probability that the first surgery is not successful, guys? If it is 85% for success, what will it be? Exactly. And what's the probability of the second one not being successful? And what's the probability of the third one not being successful? Well, it's not going to be bad news for the surgeon. You will see the probability is going to be very low, guys. Watch. Zero 0.15, 15, 15. There you go. You should not be surprised if that's the answer. The chance is 0.003. It's a 3 out of 1,000 chance that this surgeon will perform 3 surgeries and none of them will be successful on that same day. That will not happen, guys. It's very low probability. Okay. So I will stop here and we will continue tomorrow. We will wrap up chapter 3 tomorrow. I just need another 45 minutes with chapter 3, guys, and then the rest of it we'll talk about the test. So please attend tomorrow's